when you set C1 to C2, you get something called a coupling equation that relates the two material indices, rho Cm by sigma C and rho Cm by square root of E. What is the advantage of this coupling constant that we've identified over here? Suppose we plot M2 versus M1, the two material indices, on a log-log plot. Right? So in that case, this coupling constant, which is given by this expression over here, is your intercept. Mainly, if you use just the performance index based on one of the constraints, for each value of F and H, you will get a different property and a different value and a different material solution. You reconstruct those plots if you just plot C1 versus C2. Okay. But if you plot this M2 versus M1 in a log-log scale, you can account for different value of F by H square, given that the square root of pi by 2 is a constant. Then you can evaluate the consequences of different designs for different loads and different column heights without having to reconstruct the plots. Let's put this into practice. In this particular case, M1 being rho Cm divided by the compressive strength, sigma C, is on the x-axis, and the second material index, based on the buckling constraint, is given on the y-axis. It's a log-log plot. So in this plot, the intercept of any given line represents the coupling constant. In this case, it was proportional to F by H square. For small values of F by H square, in this case would be, let's take a situation where you have a load of 0.1 meganewton and a height of 3 meters. And the second case, a load of 10 meganewtons and a height of 2 meters. So you have one case where you have a larger value of F by H square, and in the second case, a smaller value of F by H square. On any given line, the lowest lying point, right, represents the lowest cost that satisfies those constraints, the combination of the two constraints. In one case, we would see that probably a cast iron is the best solution for large F by H squares. For smaller values of F by H square, the cheapest material would be more like a concrete. So you begin to see that while you have a plot of M2 versus M1, and you have all these this bubble chart created for these bubbles of different materials, right? Mainly you can still, by using slopes that are determined, in this particular case you're looking at a slope of 1, and then you're varying the intercept in this log-log plot, you can go through various design combinations that not only vary the material based on the material index, it also varies according to the geometry, changing H, and the structural constraint, so varying the load F. You can look at the combination of structural constraint, geometrical constraint, and material constraint in a same plot. This is a situation when you have two constraints with one objective of minimizing cost. Cost being minimum will be at the lower left-hand side of any situation.